So it gives me great pleasure to re-welcome Professor Stefan Willitsch from the University of Basel to give his second talk on cold molecular ions and traps, methods and applications. Over to you, Stefan.
Thank you very much, Sadiq. It's a great pleasure to be with you again, and I thank you all for joining me for this second lecture. I have sent the organizers an updated version of my slides here because I've added a few more things, and I hope they will upload them to the website soon, so that you can also upload your notes if you like to. Okay, so my second lecture will deal with cold ion neutral interactions. So during my first lecture, we have been talking about cold molecular ions, the basic techniques behind them, and mostly applications in spectroscopy and in quantum technology. And during my second lecture, we will talk about cold ion neutral interaction with particular emphasis on ion-atom hybrid systems, as the organizers have asked me to specifically talk about that. So that will be the focus of the talk. And I will start with a short introduction to the theory of ion-neutral interactions, insofar as we will need it to understand the various experiments that I will be talking in the second half of my talk. Okay, so let's talk about ion-neutral interactions a bit. And I'd like to start with recapitulating some elements from classical collision theory, just to introduce the salient concepts and also quantities that we will need later on. So just to start this, let me remind you that there are three types of collision events that are important, right? So when I talk about interactions here, what we mean with interactions is in the end, well, this always boils down to collisions, right? So we'll be talking about collisions. And there are three classes of collisions that are relevant for our topic here. The first one is elastic collisions, right? And this is collisions where the total kinetic energy and therefore also the internal state of the collision partners are observed, right? So like in a classical billiard game, if you like. Then we have inelastic collisions. And this is the case when the total kinetic energy and the internal state of the collision partners can change during the collision and the interaction, but their chemical structure is still conserved. And then in the end, we have reactive collisions, and that is the most complicated of all of them. And this is where all of this changes, right? Kinetic energy changes, internal state changes, and also the chemical structure can change. And we will encounter all three types of these processes over the course of this lecture. So let me focus to begin with on elastic collisions. Because that's the simplest case we can have, and I will use this example to introduce some of the salient. Let's, for the sake of the argument, first consider just the collision of two structureless particles, right? You can think of this as a classical billiard game, or if you will, two atoms, structureless atoms that collide with one another. And we are always dealing with these problems within the center of mass frame. Yeah? So we are not in the laboratory frame, but we transform the whole problem in the center of mass frame, where we separate the collision problem into a motion of the center of mass of the two collision partners and their relative motion. And for the collision dynamics, what is always important is just the relative motion of the two particles. Okay, so what you see here is a cartoon of a classical collision trajectory in the center of mass frame. So what we have here is we have essentially two coordinates that suffice to describe this problem, because essentially it has cylindrical symmetry. So that is the distance or the relative position vector between our two particles, right? And for the sake of these cartoons, you can picture it as, you have one collision partner here in the center and the other one approaches on this trajectory, right? Just for the sake of visualizing it. But remember, again, this is in the center of mass frame. And then we have an initial velocity vector that describes the approach of those two. So we then have an orientation angle, which is the angle between the relative position vector and the initial velocity vector. And you see here the collision trajectory, right? And during such an elastic collision, what typically happens is, I mean, the velocity vector gets deflected by a certain deflection angle. What is also an important quantity is this impact parameter here. And the impact parameter you can understand is if you draw a parallel line between the initial velocity vector, right, and the line that goes to through the center of the of this coordinate system, then you have here the asymptotic perpendicular distance between these two lines is what is called the impact parameter. And this impact parameter will play an important role later on. Okay, now let's have a look at some salient physical quantities. One of them is, as usual, the angular momentum. And in classical mechanics, the angular momentum L, the vector, is defined as mu times v vector product with r. Mu is the reduced mass of the collision, v is the relative velocity vector, and r is the relative position vector. Now, if we want to calculate the magnitude of this angular momentum, then we have to calculate the magnitude of this vector product, and we can express this by this identity. So the magnitude of this vector product can be cast into this scalar product here. We have mu times v scalar product with r sine of psi. Now, if you look at this expression here, r times sine of psi, then you realize that this is nothing else than this impact parameter, right? So we can express the magnitude of this angular momentum as mu times v times the impact parameter b. Okay, so this means that L is proportional to b. The magnitude of this, the angular momentum of this collision is proportional to b. Yeah. So, and since angular momentum is conserved here, so L before the collision is the same as L after the collision, this means that we can calculate the angular momentum for this entire process with this simple relationship. Okay, so this is an important result. So the other salient quantity is, of course, the total energy in this whole problem. And of course, we have kinetic energy. Then we have potential energy. This is the energy that comes from the interaction between the two particles, the interaction potential. So that is nothing surprising. What may be not so obvious in the first place is that we also have a third component, and that is the centrifugal energy. And the centrifugal energy, well, this is the energy that is associated with a rotational motion. And what is the rotational motion here? Well, the rotational motion is essentially, this is the rotation of this relative position vector about this orientation angle psi over the course of the collision. Okay, so in general, with collisional process, there's also this rotational component involved, and that is what gives rise to a centrifugal energy, right? In classical mechanics, the centrifugal energy can be expressed by this term here. So it's 1/2 mu times r squared times psi dot squared, and psi dot is the time derivative of this orientation angle. So it's the angular velocity by which this orientation vector, the relative position vector, is turned during the collision. So we can now use this result, namely that the angular momentum can be expressed as mu r squared times omega. And so we can insert this into the centrifugal energy and derive at the result that the centrifugal energy can be cast into 1/2 L squared over mu r squared. So in other words, the centrifugal energy is not surprisingly a function of the collisional angular momentum. So for the total energy, we arrive at this result then. We have the kinetic energy, we have the potential energy, we have the centrifugal energy. And those two last terms, they're usually lumped together to a new effective potential, a centrifugally corrected potential, right? Because the centrifugal energy disappears essentially as a contribution to the potential part of the problem. Okay, so what one is also interested in is, of course, cross sections, right? And in a simple hard sphere approximation, so the billiard ball game, if you like, one can express the cross section simply as pi times b squared max. And this b squared max is the maximum impact parameter at which a collision still happens. And what one often measures in an experiment is actually a rate constant, how fast the process happens, at which rate the process happens. So the constant associated with this quantity, and this rate constant can be expressed as sigma, the cross-section, times the relative velocity. Okay, so these are important quantities that become relevant in experiments. So let me say a few more words about this centrifugally corrected potential, because this will play an important role in what comes later on. So I've already said that the centrifugal energy, that's the energy that's taken up in the rotation of the position vector. And the collisional angular momentum, well, this is the associated angular momentum with that rotational motion. So it's the angular momentum that goes along with the rotation of r about psi. And if you now look at the form of this effective centrifugally corrected potential, then you see it has these two components as discussed. If you look at typical interaction potentials between atoms, but also between molecules, then they typically have qualitatively this sort of shape, as a function of the distance between the two particles r. They have an attractive part, which is usually long range. And if the particles come too close together, then there is a repulsive part, which essentially stems from qualitatively from the repulsion of the electron clouds around the particles when they come too close together. So we have attractive and repulsive parts in the interaction potential. However, if you look at the centrifugal part of the potential, then this is always positive, meaning repulsive, right? Because all these quantities are always larger than zero. So this means that whenever we have centrifugal energy, it adds a repulsive component to the whole problem. And this can be seen here. So here, this curve is just the interaction potential without any centrifugal part. And if L, the angular momentum of the collision, becomes non-zero, then we see that the barrier builds up here. And that is the infamous centrifugal barrier that arises because of the angular momentum in the collision. And the larger L, right, the larger this barrier becomes. And in an extreme case, the effective potential becomes totally repulsive of the collision. So that means is that this centrifugal energy plays an eminent role in collisional processes. And we will see more details over the course of this lecture. Okay, so let's talk a bit more about interactions between ions and neutral. In other words, let's talk a bit more about this interaction potential V of R. And our topic is ion-neutral interactions. And thankfully, one has to say, it turns out that ion-neutral interactions are very often governed just by the long-range part of the interaction potential, meaning the attractive long-range part that I have been referring to. And this long-range part can usually be expressed as a power series in the internuclear distance. This is a multipole expansion of all these long-range interactions that one does here. As a function of the internuclear distance. And one can see that, we have terms in R squared, R cubed, R power 4, this should be a superscript here, and so forth. And the task is now to just figure out what these different coefficients are for different scenarios of collisions that one has. So the first term here, there would also be a C1 term, right? But the C1 term would just be a Coulomb interaction. And since we are dealing with ion-neutral interactions, this term is not relevant. So the leading term is then, under certain cases, the C2 term in this series expansion. And this term corresponds to a charge dipole interaction. So the interaction between the charge of one of the collision partners and the permanent dipole moment in the other collision partner. But for this to be non-zero, the other collision partners needs to have a permanent dipole moment. And in other words, this is usually a case when we have molecules, because atoms don't have permanent dipole moments. So, and then in this case, the C2 coefficient can assumes this form. So we have the dipole moment of the neutral molecule, and then there is, of course, an orientation dependence. If that is the charge, if that is the dipole moment, then of course it depends on how the dipole moment is oriented with respect to the charge. Yeah, so this is the leading term if you have an interaction between an ion and the polar molecule. If the molecule is not polar, or if it is an atom in certain states, then we do not have this term, and the leading term is then this C3 term. And the C3 term corresponds to an ion quadrupole interaction. Yeah, so this is where the charge of the ion interacts with a quadrupole moment in its counterpart. And this is the case when the interaction partner is an atom in a non-spherical symmetric state, meaning a PD or an F angular momentum state, or if it is also an apolar molecule, right, which doesn't have a dipolar moment, but then it usually has a quadrupole moment. And if it's a molecule, then the C3 term, this is usually expressed in this form here. So Q is the quadrupole moment of the neutral molecule, right? So if we stick to a linear molecule, then this is usually taken as the largest entry in the quadrupole tensor. And then again, we have an orientation dependence here expressed with this cosine squared of theta term. If the counterpart is an atom in a PEDF or higher angular momentum state, then one can calculate the C3 term from spherical tensor algebra and derives at an expression like this. And one sees here that one has a Wigner-free J symbol in this expression and the reduced matrix element of the quadrupole moment tensor. Okay, so with this you can calculate this multipole coefficient C2 and C3. If neither of these terms applies, then the next leading term is the C4 term. And this arises because of an ion-induced dipole interaction. Yeah, and this is the leading term if the neutral counterpart is a structureless polarizable particle, yeah, say an atom in an S state. Yeah. Or it could also be an apolar molecule with a very small quadrupole moment, which can be neglected for practical purposes. And this C4 term is then given as 1/2 times alpha, and alpha is the scalar polarizability of the neutral. This is also often called the Langevin interaction, and this will play again also an important role later on. I should also add that usually the C4 term also contains an anisotropic component, right? Because nothing really is really perfectly structured. Okay, but this is certainly the leading term, and this is the one that we will be considering henceforth. Okay, so I said ion-neutral interactions can very often just be understood in terms of this long-range interaction. And if that is the case, right, then collisions between ions and neutral often follow what is called capture dynamics. Yeah, and that is exactly what this refers to, namely that the collision is completely governed by the long-range interactions, and short-range interactions between the particles then do not play a role. And one of the most important cases of such a capture processes between ions and neutrals is so-called Langevin capture. And that is the case when the long-range interaction is dominated by this Langevin interaction, so the ion-induced dipole interaction, the C4 term. Okay, so how can one understand these capture processes? And this Langevin capture is usually treated within the framework of classical collision and capture theory, and this can be understood rather simply, actually. So what I've plotted here is again the effective interaction potential that we have discussed, so the interaction potential plus the centrifugal potential as a function of the internuclear distance. And they only focus on the long-range part, right, where we also see the centrifugal barrier. So for a successful collision to happen, the two collision partners essentially then have to overcome the centrifugal barrier. Okay, so remember, that is the form of this effective potential. We have the centrifugal part, we have the interaction part. This one is usually attractive, as we have seen. And this one is always repulsive and leads to the centrifugal barrier. And what is now important to remember is the expression for the classical angular momentum, right? This is given by mu times v times b, and b is again the impact parameter. So for a collision to be successful, meaning that the two particles can come close to another, right? They have to surmount the centrifugal barrier, right? So this means that the collision energy with which the two particles come in needs to be high enough so that they can surmount the centrifugal barrier and come to close interparticle distances, right? Where then the collision really happens. So for this to happen, right, so we have this condition, right? So this means that the collision energy, right, must be at least equal to the maximum of the effective potential, right? And since the effective potential is linked to the angular momentum of the collision, and the angular momentum is linked to the impact parameter, there is a maximum angular momentum and therefore a maximum impact parameter at a certain collision energy which fulfills this condition. Okay? So, and then from this condition, one can work out what this maximum impact parameter needs to be so that the height of the centrifugal barrier is just equal to the collision energy. From that, one can work out the maximum impact parameter, and then from the maximum impact parameter, one can work out the collision cross-section. And from the collision cross-section, one can then work out the rate constant for the collision. And with that, one has everything that one needs already. Okay? So the picture that we have here is that in this classical capture theory, the collision energy needs to be high enough in order to surmount the centrifugal barrier in the effective potential. This gives me a condition for the maximum impact parameter that the collision can have. And the maximum impact parameter is then linked to the cross-section and the cross-section to the rate constant. So that is the rationale. So if now this long-range interaction potential is dominated by the Langevin interaction, meaning the ion-induced dipole interaction, and I give it again here, this time in SI units, then one can work out from this collision the cross-section and the rate constant for this specific potential. And one finds that the cross-section has this form and the rate constant has this particular form. And now let's just focus on the rate constant for a moment. We see that it is actually quite simple, right? It's the square root of pi times alpha prime. Alpha prime is the polarizability volume of the neutral. Yeah, so it's the polarizability divided by 4 pi epsilon naught. E squared, this is the elementary charge squared, epsilon naught is the electric field constant, and mu is the reduced mass of the collision, right? So we only have two parameters, two system-specific parameters that play a role here, the reduced mass, right, and the polarizability of the neutral. So it's a very simple expression for the rate constant that one gets here, and the important thing to note here is also that it is independent of the collision energy, and therefore also independent of the temperature, the collision temperature, right? So we have, meaning if we have Langevin capture dynamics in an ion-neutral collision, then the rate constant is constant with temperature and therefore also with collision energy. So that is an important result here. Okay, so that was classical collision theory and applied to classical capture theory. Let me just say a few words about the quantum treatment of these processes. I mean, this is a topic about which I could lecture an entire term. Let me just recapitulate a few important points here. So if we cast the same problem, right, elastic scattering of two structural particles into a quantum mechanical framework, then, okay, we have to set up the Schrodinger equation for this problem. And the Schrodinger equation in spherical coordinates is given here, right? So it's again the Schrodinger equation in terms of R, and there is also the orientation angle theta, psi as we have called it before, involved. And this is ingrained here in the angular momentum operator. So we have here, again, the kinetic energy operator. We again have a term that corresponds to the centrifugal energy of the problem. And again, we have the potential energy. And as a matter of fact, this Schrodinger equation that you get here, that you have here, right, is the same Schrodinger equation that you also have for a diatomic molecule. Only that in this case, we are not interested in the bound solutions of this Schrodinger equation, meaning the bound states of this molecular system, but in the scattering states, right? So those solutions with a positive energy. But otherwise, it's the same Schrodinger equation. So it has the general solution of this form. Yeah. So you again, so what you can do is you can separate the solution into two parts: an angular part, and the angular part turns out to be the Legendre polynomials as a function of cos theta because of the cylindrical symmetry of the problem, and the radial part, right? And now the interesting part of the solution is this radial part. We have again angular momentum. It's now quantized with quantum numbers 0, 1, 2, and so forth. Now, we all know what Legendre polynomials look like. The interesting question is now, what do these radial functions look like? And if one solves the Schrodinger equation, then one finds as an asymptotic solution to these radial functions these sort of sine functions. These are essentially the asymptotic form of Riccati-Bessel functions that one gets as a solution to this case. And I should say, we are only interested in asymptotic solutions here. Because, I mean, in a typical experiment, any detector that we use to detect the outcome of collision events is far away from the microscopic collision region where the two particles collide with one another. So what we essentially can measure is the wave function far away from the collision centers. And this is why we are only interested in the asymptotic form of the solution. And this is the asymptotic form of the solutions that we get. So what we see here is that it's this sine function, right? And it has as arguments a term k times r. Yeah, and that is a bit reminiscent of what we also get for a free particle wave function. But then we have here two phase shifts, effectively. One of them is proportional to the angular momentum quantum number L. And it is actually a phase shift that arises because of the centrifugal term in the effective potential. And then we have another phase shift, eta L, and that is called the scattering phase. And this scattering phase is a phase shift in the wave function that arises because of the interaction potential V. Okay? So essentially what this means is that, yeah, I mean, the scattering manifests itself as phase shifts in the wave function. And it further turns out that it is this scattering phase shift which is then linked to the scattering cross-section. Now, the scattering cross-section can be formulated as something proportional to a sum over all angular momentum states times the sine squared of the scattering phase shift. So essentially, one needs to work out what the scattering phase shift is. And one can further show, yeah, and you can read this up, for instance, in this paper here, that in the semi-classical limit, meaning if we have large values for the angular momentum quantum number L, then the scattering phase shift can be approximated by this rather simple expression. So we assume that, again, that our interaction potential is an ion-induced dipole potential. So we only consider the C4 term in this multipole expansion. E is the collision energy, and L is the angular momentum quantum number. So, and if we have this expression for the phase shift, then based on this, one can calculate a semi-classical expression for the scattering cross-section. And the important thing to realize here is that this in the end scales with the collision energy power minus 1/3. So we have an E power minus 1/3 dependence of the elastic scattering cross-section in the semi-classical limit. And what is shown here is the validity of this approximation actually as a function of the collision energy, that one can see that only at the lowest collision energy, where we only have few partial waves, meaning few angular momentum. So if the angular momentum of the collision is very low, then we have appreciable deviations of this semi-classical expression, which is the dashed line here, from a rigorous quantum solution of the whole problem. Yeah. So meaning, especially in the regime that we will be working, so that is millikelvins and above. Typically, for ion neutral interactions, we are still in the semi-classical limit with many partial waves. Okay, so I think this is a good time to ask questions. That is everything I wanted to recapitulate about ion neutral interactions and collision theory. Are there any questions at this point?
Stefan, yes, there's one question in the chat, which
Yes.
is this expression is for elastic or total cross section?
Elastic.
Right. Okay. I don't see any other questions. Maybe I can kind of talk to you later about this whole business, but carry on, please.
Yes. Okay. Good. Right. So let us now come to a few experiments. And I already said that I will focus in my talk on ion atom hybrid systems. And so over the course of this school, you have heard about atom traps, ion traps, molecule traps. Now let's talk about hybrid traps. And a hybrid trap is a combination of an ion trap with an atom trap. And that is an experiment that has been originally been proposed in a series of papers by Robin Coté and Winthrop Smith in the early 2000s. And they were first implemented, the sort of experiments were first implemented a bit more than 10 years ago, starting with a seminal paper by Vladan and Willitsch's group in 2009. And where they combined a surface electrode ion trap with a magnetooptical trap. And since then, many different groups all over the world have come up with similar experiments. It's typically linear pole traps that are combined with magneto-optical traps, or linear pole traps with magnetic traps and or optical dipole traps, in which one can keep the atoms, and sometimes even in the form of a Bose-Einstein condensate. So this has now become a thriving field on its own. There are, I don't know, between 10 and 20 groups all over the world who have experiments like that, and there are many more groups who do theory on this kind of processes. So it's become a thriving business in itself. There are also already a range of review articles now on this topic, which I invite you to delve into if you're more interested in that. So to give you some ideas about what these experiments look like, let me say a few words about the experiment that we have in Basel. Our hybrid trap experiment consists of a linear radio frequency ion trap, very similar, completely the same actually as the ones that I have introduced in my first lecture. And that is superimposed with a magneto-optical trap. So a magneto-optical trap consisting of two coils that create an inhomogeneous magnetic field, quadrupolar magnetic field. We then have laser beams in an optical molasses configuration, which then cool atoms in this quadrupolar magnetic field. And in our case, it's rubidium atoms, which are kept in this mod. You see here a fluorescence image of these rubidium atoms, which are kept in the mod and superimposed with the ions. And then on the ion side, we have calcium ions. Sometimes we also have barium ions, which are laser cooled in here. But then we can also load molecular ions into this trap to look at molecular processes, and this is what what I will be talking about at the end of my lecture. Okay, so I would now like to talk about a few examples of processes that one can study in these experiments. And what it turned out is that there's a rich collision physics. right? And also chemistry, as a matter of fact, that one can observe in these experiments. So let's start with a few simple things, right? Let's talk about elastic collisions between the ions and the atoms in such an experiment. And this is one of the very first results that came out of this field from Johannes Eckert-Enschler's group in Ulm, where they had an experiment where they trap barium ions together with rubidium atoms. And of course, what the simplest types of collisions that can happen here are elastic collisions. And this is what they have been studying here. Yeah, what we see here is the number of atoms that are held in a cloud of ultracold atoms that is superimposed with, in this case, it was a single barium ion. And one can then see that the number of atoms decreases as a function of the interaction time with this barium ion. So what happens here is that we have collisions between the atoms and the ion in the trap. And the atoms are usually much colder than the ions in the trap. And moreover, the ions, they also have micromotion. We have already briefly touched upon this last time. This is this fast oscillating motion that an ion assumes in an RF trap. And so the ion is more energetic than the atoms, and by elastic collisions between the two, the ion can impart then kinetic energy to the atom with which it collides. And these atom traps, they are usually not too deep, right? So if the atoms are too energetic, they fall out of the trap. And this is what we are seeing here. And so what they have done is they have moved the ion in space through the atom cloud, and depending on what sort of atom cloud they had, either a thermal cloud or a partially condensed cloud or a fully Bose-Einstein condensed cloud, then they could essentially map out the density profile of this atom cloud by just looking at the loss of the atoms through the collisions with the ions in this trap. Okay, so this is elastic collisions going on, which essentially lead to an ejection of the atoms from the atom cloud. What this can actually be used for is to minimize the micromotion of the ions, right? I mean, if you minimize the atom loss when you overlay the atom with the ion, then as a function of the ion position, you can use this to try to place your ion on the RF null line of the trap where the micromotion is ideally zero, and in this case, minimize the micromotion, excess micromotion in the system. And that is shown, for instance, in this paper. Okay, so these elastic collisions, they can also be used for sympathetic cooling of the ions by the atoms, because what these atoms are, they are nothing else than a buffer gas, a cold buffer gas, right, in which you immerse a typically hotter ion. Okay, so by collisions of the cold buffer gas with the ions, you can, you can cool the ions, and that is shown here in this work by Michael Köhl's group from a bit more than 10 years ago, where they determined the ion temperature as a function of the interaction time. In their case, it was ytterbium ions with ultra-cold rubidium atoms. And as a function of the interaction time, they saw that the ion temperature decreases. And because of sympathetic cooling of the ions by the atoms. Buffer gas cooling, if you like. It's nothing else than that. Okay, so that are simple elastic collision processes that can happen here, right? You can use these ultra-cold atoms to cool the ions, and you can also use the ions to eject atoms from the trap by elastic collisions. Now let's look at a bit more, let's say, more gory phenomena. And it turned out that in this variety of different ion atom hybrid systems that have been implemented over the last decade or so, maybe not to everyone's delight, it turned out that in many of these systems actually a very rich chemistry happens. So we not only have elastic collisions or maybe inelastic collisions, but we really also have reactive collisions going on here. And moreover, it turned out that what is very important is the role of light in these experiments. Because, yeah, I mean, the ions are very often laser cooled in these experiments, or they are laser cooled to start with for sure, but also during the operation of the experiment. The atoms are laser cooled if it is a MOT experiment, so photons are always present, right? And therefore excited states of both the ions and the atoms are present. And this turned out to play an important role in many cases. So I'd now like to start this topic with presenting a few results from our group. Yeah, from predominantly on the calcium rubidium system. And this is a typical scenario that you have in our experiment in Basel. So we have a calcium Coulomb crystal that is immersed in a cloud of ultracold rubidium atoms in the MOT. And what you can already see from this image here, so you see both particles are fluorescing. So this means both of them are laser cooled, right? So both the ions and the atoms are laser cooled, and therefore there's always population of both the ions and the atoms present in the excited states. So what we then saw in the very first experiments that we did, and this was now also about 10 years ago, we saw that the calcium ions would disappear from the trap as a function of time. And so this is shown in this image here. So this is just focuses on the fluorescence of the calcium ions. And one can see that this calcium Coulomb crystal shrinks in size over the time scale of a few minutes. And one can further see that this crystal gets characteristically flattened. And this flattening essentially is caused, as we've already discussed in my first lecture, is caused by the sympathetic cooling of molecular ions or other ions, non-fluorescing ions, I should say, which are formed by this process. The interesting question is now, of course, okay, this is clearly some reactive processes that's going on, right? I mean, the calcium ions, they are transformed into another chemical entity, whatever it may be. So the first question, of course, is what is this chemical entity? And one can now do is one can turn the ion trap into a mass spectrometer in a very similar way as we've already discussed in my first lecture. So one can apply a small tickle voltage to an electrode in the ion trap to resonantly excite the ions in the trap. So scan the frequency of this tickle voltage and then map out resonant excitation of the ions, which depend on the mass of the ions in the trap. So in this way, you can take a mass spectrum of the species in your trap. And this is shown here. So before the reaction, we just see a single resonance, and this corresponds to the calcium ions, which are present in the beginning of the experiment. But then in the end, we take a mass spectrum, which looks like this. And this has now 4 peaks. And we identify these 4 peaks with the emergence of well, there are still a few calcium ions left, but we have 3 more species that emerged over the course of these collisions. And we attribute them to rubidium 2+, calcium rubidium+, and also rubidium+. Now, how on earth can one get these sort of species here? And for this, one now needs to turn to theory and look at what can actually happen during these collisions. And what you see here are potential energy curves, so the interaction potential between the collision partners for various states of the collision partners. So we have rubidium in its ground state and calcium ions in its ground state. Yeah, so this is the lowest collision channel that we can have if both particles are in the ground state. And associated with that, we have that sort of interaction potential, right, which is this thick red line. However, what one has to realize is that this here is not the lowest state of the collision system. Yeah, rubidium has a lower ionization energy than calcium, right? So this means that there are charge transfer states which have a lower energy than our entrance state here. Yeah, so these are states where the charge has hopped over from calcium to rubidium, or an electron has hopped over from rubidium to calcium plus, if you like, and they are lower in energy, right? So this, the absolute ground state, is where we have a rubidium plus ion and calcium, neutral calcium atoms in their ground state. And then there is still another asymptote below our entrance channel, and this is where the calcium has been excited, or one electron in calcium has been excited to the 4p orbital. So, and with every one of these asymptotes, we have, of course, molecular states associated with them, right? And these molecular states, they go along with their own potential energy curves, as one can see here. And during the simplest case of the collision that we can have, right, where the rubidium atoms and the calcium ions in their ground state collide with one another. So then during the collision, we come in here, right, as a function of the internuclear distance. Those two come close to one another. And at some point, they reach a region where we have a crossing with this green dashed curve here. And that is a potential energy curve that is associated with this charge transfer state. And whenever we have a crossing between potential energy curves, right, then this is a region with an increased degree of interaction between the states. These are so-called non-adiabatic interactions. And through these interactions, the collision system can hop over from one curve to the other. Yeah. And if it hops over to the green curve, right, then after the collision, the two particles can depart again on the green curve and then arrive at this asymptote. Yeah. And there you see at this asymptote, we had a charge transfer, right? So, and this explains in part the observation of these rubidium ions in the trap. But there is more. We also have, we can also have radiative processes, right? I mean, this is an excited state, right? And during the collision, in principle, a photon can be emitted, right, down to the lowest curve. And depending on whether a bound molecular state on the lowest potential energy curve is populated, or if a scattering state is populated associated with this lowest energy curve, we have either radiative association, so the formation of molecules, or we have radiative charge transfer. Yeah. So if you populate a scattering state, then the system is not bound, right? So the particles can depart again and again reach this asymptote. So we have rubidium plus again, right? And if a bound state is populated, well, then we have a bound molecule, and that then leads to the formation of calcium rubidium plus. Okay, and the rubidium 2 plus that we also observe in this experiment are most likely due to a chemical process where this calcium rubidium plus further reacts with rubidium atoms in the trap. Okay, so we have three processes that can go on here in principle: non-radiative charge transfer at these curve crossings, radiative charge transfer, and radiative association. Okay, so this is a rich physics that's going on, if you like. One can now also, ask further questions. For instance, what is the rate constant associated with all these processes, and in particular, what are the rate constants of the different collision channels that we have? I mean, we have collisions between ground state calcium plus and ground state rubidium, which is what I've just discussed. But then we also have collisions with excited state calcium and rubidium. And we can also have in calcium, we have two excited states present. Actually, we also have this double D3 half state, right, which is also partially populated in the experiments. So, and what we now asked in these studies is, okay, what is the rate constant associated with collisions of ground state rubidium with calcium plus in any one of these three states? And it turned out that collisions with calcium ions in these excited p states are clearly the fastest, right? By more than 2 orders of magnitude compared to collisions in these other two states. Now, why is that? Why do we have such a pronounced state dependence of the rate constants of these collisions? So a qualitative explanation for this can be gleaned from the full well, it's actually not even full, but from a fuller potential energy diagram of this collision system. So here on the lower part, these are the potential curves that I have showed you before, right? But there are many more if you increase the energy, right? And here, what you see here is the asymptote rubidium in its ground state with calcium plus in its 4p state, which corresponds to this rate constant here. And you see that below this asymptote, right, you have many, many more asymptotes, right? And moreover, what I show you here in this part of the figure are only the states of singlet sigma symmetry, molecular states of singlet sigma symmetry. There are triplets, there are pi's, there are delta states, right? So if I would plot them all, right, there would not be much white left on this plot. So this is a very dense energy level structure that we have in these collision systems. And what one can already glean from looking at this here is that we have if we have a collision on this curve here, if the two come together, then we have many crossing points. In this case, they are drawn as avoided crossings with other molecular states, which give multiple opportunities for non-adiabatic charge transfer. And of course, still, I mean, there can also still be radiative processes, and you can radiate down to a variety of different states down here. So there are also many opportunities for radiative association and radiative charge transfer. And working this out qualitatively from theory is extremely challenging. It has not been done, but just from a qualitative picture that we get here is that the number of possible reactive channels, right, in collisions in excited states is very high, and this is probably the reason why we observe such a considerably larger rate constant in the excited channels compared to the lowest channel. Okay, so another interesting question that one can ask now is, okay, so what is the collision energy dependence of these processes? And so we measure now these rate constants as a function of the collision energy. And what you see here, let's just focus on calcium plus rubidium again, is now a channel averaged rate constant, so averaged over all these collision channels, as a function of the average collision energy from about 10 millikelvin up to about 10 Kelvin. And one can see this is essentially flat. So a few words on how we tuned the collision energies in these experiments. What we did is we essentially imparted a well-defined degree of micromotion to the ions, right? And so we essentially we pulled them off the RF null line to give them excess micromotion, and so that the average collision energy is determined as a matter of fact by the average micromotion energy of the ion. Okay, and we did a similar experiment for barium plus rubidium and observed a very similar result here. So, and what one can see here is this, okay, the collision, the rate constant is essentially constant with collision energy for both of these systems. And this is a bit reminiscent of what one gets from Langevin theory. Okay, Langevin theory predicts an energy independent and therefore temperature independent rate constant. The magnitude of the rate constant is smaller than the Langevin rate constant. It's important to realize here, but the energy dependence is very reminiscent of what we get with Langevin theory. So how can one understand this? And one can understand this if one looks a bit closer into the quantum mechanics of these different processes that we are dealing with here. So radiative charge transfer, radiative association, and non-radiative charge transfer. So it can be shown that the cross sections for these processes, and this is essentially discussed in this seminal paper by Alex Daldano and Siegelman here, can be cast in expressions like this. Yeah. I don't want to go into too many details here. Suffice to say is that the cross section is essentially given by a sum over all angular momentum quantum numbers that we have here. Then we have an integral over all, so for radiative charge transfer now, we have an integral over all final energies of the charge transfer product. Then we have an omega power 3 term, right? This is a bit reminiscent of what you have also in the Einstein A coefficient. So there is an omega power 3 dependence, and omega is the angular frequency of the photon that's emitted. So it's the same as we have in an Einstein A coefficient. But then we also have this transition dipole moment matrix elements. Okay, so this is essentially the dipole moment matrix element for the optical transition between the initial state and the final state. Right? Remember, these are radiative processes. Okay, and for radiative association, we have analogous expressions. Okay, so but the important point is here that we have these transition dipole moments that play a role here. And for non-radiative charge transfer, we have an expression. And here the important point are these non-adiabatic transition probabilities, right? That happens at the curve crossings between two molecular states. And at these points, as I've already mentioned, this is where the transition from one curve to the other predominantly happens. Okay, so now let's focus on these radiative processes, and the similar argument can also be made then for the non-radiative charge transfer processes. So what one realizes with the example of calcium plus rubidium is that that these transition dipole moments, right, which drive the radiative transitions, they are all localized at short range, okay, because the wave functions need to properly overlap of the initial state and the final state, right? And they do this best at short range. And what I show you here in the upper part of this plot is the value of these transition dipole moments, right, for radiative transitions in calcium rubidium that we have discussed before. And let's focus on this red thick curve, right? That is the transition dipole moment for a transition from our entrance channel, calcium plus in the ground state plus rubidium in the ground state, colliding with one another, and then radiating down to the absolute ground state of the system, which is rubidium plus calcium. Okay, and so you see these transition dipole moments, they only become appreciably large at short internuclear distances. So in the lower part, I show you again the potential energy curves, right? It's the same ones that I have showed you before. So we come in here on these potential energy curves. Here we have crossing points with another state. Here non-adiabatic charge transfer can happen. And here at close internuclear distances where these transition dipole moments become large, we can then have radiative transition down to the absolute ground state. Now, you realize that in the region where these transition dipole moments are large, we have the potentials associated, or I should say the potential. We are already deep in the potential well associated with this with our entrance channel. Okay, so this can't be seen here on this scale, but the well depth here is on the order of 1,000 Kelvin. Okay, so meaning when these radiative processes kick in, our two collision partners are already sufficiently close so that they are around the region of the bottom of this well, at which point they already have been appreciably accelerated by this interaction potential. So we come in here at very low collision energies, 10 millikelvin, 100 millikelvin, 1 Kelvin or so. But classically what happens is that the closer they get is, then this potential starts to accelerate them, right? And then they come to close internuclear distances, and then they can either undergo non-adiabatic charge transfer or these radiative processes. But locally here, they have become fast. Yeah. So meaning the curvature, let's put it in other words, the curvature of the wave function in here, right, is predominantly determined, right, by the depth of this well, right, and not by the asymptotic collision energy anymore. So meaning that whenever we have the case that we have an appreciably deep potential energy well, right, out in the region of which these reactive processes happen, then it doesn't really matter whether the asymptotic collision energy was 10 millikelvin, 1 Kelvin, or 10 Kelvin, right? If the well depth here is 1,000 Kelvin. Okay, so because the properties of the wave function will then mostly be determined by the depth of this well, and that explains the insensitivity of the cross sections and the rate constants, or I should say the rate constants, to the asymptotic collision energy that we observe in these systems, and this is also very nicely reproduced by rigorous quantum calculations of these processes. Okay, good. Yeah, I would say let's take a few questions at this point.
Right.
Maybe a good place to stop.
Yeah. Yes, Stefan, there are a couple of questions. So the thing is, how do you measure elastic collision cross sections in the experiments? And how do you differentiate it from non-elastic cross sections in experiments?
Yeah, that's a very good point. So in the experiments on the elastic collisions that I have shown, right, the elastic collisions have been traced by the disappearance of the atoms from the track. Yeah, but you know, in principle, also inelastic processes can have state-changing collisions. Yeah, which affect the ion, and which you would not notice if you didn't probe the ion explicitly. Now, whether this can happen or not is determined by the structure of the ion, of course, and by the energy available, whether such inelastic processes can happen or not under the conditions of the present experiment. Yeah. But it's a good point. I mean, yeah, one always has to be careful that maybe not also inelastic processes can happen as well. So if you have reactive processes, right, like I was talking about on the last slides, I mean, then it's rather simple, yeah, because I mean, if you have a chemical reaction going on, right, then you see a chemical change in your ions, right, and then it's clear it has to be a reactive process.
There's another question: would you need C3 term in the multipole expansion to get collision rates for P and D levels?
Sorry, say again.
Would you need C3 terms?
Yeah.
In the multipole expansion to get the collision rates for P and D levels?
Yes.
Right. So
yeah, I will come back to that later, actually. But yeah, okay. Let me qualify this remark a bit. It depends on the collision energy. Yeah. They become important only, or you notice them in the experiment only at very low collision energies. And at high collision energies, they actually do not manifest themselves that strongly in rate constants. Yeah. So whether you have to include them or not depends on the specific of your experiment. But in principle, they are there, right? I mean, if you have an ion interacting with a neutral particle, with a neutral atom, right, in a non-S state, then you have these three terms in principle.
Right. We are.
Unless you are in a J equals 1/2 state.
Yeah, I think we can move on.
Yeah.
And yeah.
Okay, shall I carry on, or are there more questions?
Not at the moment.
Not at the moment. Okay, good. So these excited state processes that I have been talking about, which are very important in experiments when we have light present that excites the particles to excited states, either the ions or the atoms. They are suppressed in certain cases. And one of these cases is, for instance, the calcium ytterbium plus system that has been studied in Eric Hudson's group. And in the following way. Now, whether such a radiative charge transfer process or radiative association process happens is, it's of course important that the two collision partners come close enough, right? So that a that for instance, a bound state on the lowest potential energy surface can be populated. Now it happens that in some systems, like calcium ytterbium plus, we have a situation where the excited states are very short-lived. Yeah, in the sense that the excitation decays already before the partners can come close to one another. And in this case, the rate constants for the processes out of these excited channels, they are very low or even negligible. So what one can now do, both to prove this and play around with this a bit, is one can apply an additional laser beam, right? Which is not like the MOT laser beams that one has already in the experiment, but an additional laser beam, which is a bit detuned from the usual MOT transition, say, to excite then the system, not here in the asymptotic region, but already further inwards when the two collision partners have come closer together. And the calcium ytterbium plus, one also has a situation where one has non-adiabatic charge transfer at short internuclear distances. And this non-adiabatic charge transfer is usually not seen in normal experiments without this catalyzed laser, because the excitation that one needs in order to access this region of non-adiabatic couplings is the case before the two collision partners can come close enough so that this non-adiabatic charge transfer can kick in. But what can one do is one can now insert another laser beam that excites the system just at the point before the two particles come close to this region, thereby populate this excited state, come close again to this to this non-adiabatic coupling region at which this charge exchange can happen. And then from this curve, which is populated in the experiment, right? This is this orange curve. Charge exchange can happen again, right? And then the system can then, or the two particles can depart again after hopping over to this red dashed curve to this asymptote here, which is again a charge transfer asymptote. So, and what is shown here is a result, right? So this shows the rate constant measured in the experiment for this charge transfer as a function of the detuning of this catalyst laser. And here one sees the situation without any catalyst laser. Yeah, so one measures a rather small rate constant. But then if this catalyst laser is switched on, one sees a marked decrease in this charge transfer rate constant as a consequence of the presence of this catalyst laser and the population of this excited curve during the collision. So I think this is it's a fun experiment which shows how one can play with these excited state processes and how they manifest themselves in different ways in different systems. Okay, so another topic related to this charge transfer processes is the phenomenon of swap cooling. And that is quite an intriguing cooling mechanism of ions that can happen in hybrid traps, which has first been, I would say, discovered and also explored by our chairman, Sadiq Rangwala, now also almost 10 years ago. And so the mechanism is as follows. So if you have a homogeneous hybrid system, so meaning ions and atoms of the same chemical species, say rubidium, and if you have, say, a fast ion, right, that collides with a slow atom, be it in a MOT or in another atom thread, then what you can have is when those two come close to one another, you can have a resonant charge exchange, right, which is very efficient. So essentially, the charge hops over from the fast ion, right, to the slow atom, and the slow atom becomes then a slow ion, right? And the original fast ion becomes a fast atom. Yeah. So in this way, you are left with the same ion species again. Yeah. But now it's considerably slower. And that has been worked out in this paper by Sadiq's group already in 2012. And I should also mention there is a nice experiment from Johannes Heckadenschlag's group very recently, where they also characterize these sort of processes in detail experimentally. So, and also quite an interesting phenomenon that can happen in these hybrid traps when you have very dense clouds of neutral particles is three-body processes. And that has been explored in quite some detail in Johannes Heckadenschlag's group in Ulm, in experiments where they looked at both rubidium plus and barium plus ions in ultracold rubidium clouds. And what they saw is essentially that if the atom clouds are dense enough, right? So close to a Bose-Einstein condensate or even a Bose-Einstein condensate, then one can have three-body recombination. Yeah. So in a way, you can think of it as the ion present in this experiment acting as a catalyst to form a rubidium-2 molecule, right? So in a three-body collision, we can form a bound molecule out of two ultracold rubidium atoms, and the excess energy, the binding energy or parts of the binding energy that is released in these three-body collisions is then taken up by the rubidium ion. Yeah. And they explored this both as a function of the density of the atom cloud, and one can see that in order to get an appreciable free-body association probability, one needs rather dense atom clouds, yeah, much denser than one usually gets in a MOT. And moreover, what one needs is rather cold, rather low collision energies. And so this only works at very low, at very low energetic conditions. So otherwise, the molecules that are formed are not stable. Okay. That brings me to my next topic now, which is also associated with these different collisional processes in the traps. And that is the question, how well does this cooling that one sees of the ions by the ultracold atoms really work? Or in other words, are there any limits to this sympathetic cooling that is exerted by the ultracold atoms on the ions? And that is, of course, an interesting and relevant question, because cooling of ions, is a topic with a long history. And as I've already said, one cannot laser cool everything. And so if one has a general method to cool ions down to very low temperatures, in particular a prospect of reaching ultra-cold temperatures, then this would of course be a great thing, right? And in the beginning of this field, there were great hopes that one could use these ultra-cold buffer gases, right, to really prepare ultra-cold ions or different species of ultra-cold ions just by buffer gas cooling. Now it turned out that there are, things are always not that easy. And it turned out that there are some very stringent limits to the sympathetic cooling that one can reach here. And the problem is very so often with trapped ions is the micromotion. So we've encountered the problem or the phenomenon of micromotion already several times. So let me just briefly remind you what this is all about. So we have an ion in the RF trap, right? And you can decompose the motion of such an ion in the RF trap into two components. Secular motion, that is essentially, you can think of this as the thermal motion of the ions in the effective potential of the ion trap, but superimposed on that, you have the micromotion. This is a fast oscillating motion which is driven by the RF fields. And this here, to illustrate this here shows a trajectory of such an ion, a phase space diagram of such an ion in an RF trap, simulated trajectory. So the dashed red line would be the ion trajectory without the micromotion. Yeah, so this would correspond to the secular motion in the time averaged effective potential of the trap. And the red and the blue trajectory is the same ion, but now with the micromotion in the full time-dependent potential of the ion trap. And one can see the effect of this micromotion the further one gets away from the trap center, where the RF fields vanish for symmetry reason. The larger the micromotion gets, the larger the amplitude of the micromotion gets, and therefore also the larger the energy stored in the micromotion gets. So, and what one typically does in ion trapping experiments is one tries to minimize this micromotion as much as one can, meaning put the ions into the center of the trap onto the RF null line, where ideally the micromotion vanishes. So even if one manages to do that, right, as good as one can reasonably do, then in such a hybrid trapping experiment, there is still a complication there. Yeah, so the micromotion still starts to play a role because, and this has been first discussed in this seminal paper from Vladan Willitsch's group, that even if the ion is placed on the RF null line, right, at the point when some neutral particle approaches the ion, right, then the interaction between these two particles starts to pull away the ion from the RF null line, right, and in that point, at that case, it assumes micromotion again, even if the micromotion was perfectly compensated to begin with. And if then a collision happens, right, under conditions where we have micromotion, then in unfavorable circumstances, right, through the collision, micromotion energy is then coupled into the secular motion, and that then leads up to a heating of the ions. And of course, how big a problem that is, that depends on when in the RF cycle, when in the micromotion cycle the collision really happens, right? But if you average this over time, right, it turns out that you cannot really neglect this. Yeah. So that means that even, right, if you have perfectly cold, perfectly micromotion compensated ions, even if you have cooled them down to the motional ground state of the trap, and even if you have ultra-cold atoms, right, then this means that through these collisions, and if these collisions are elastic, and if you already have a couple of them, then you get the heating of the ions because of micromotion interruption. It has first been discussed in this paper, and it actually then goes back to problems that have been known for a very long time. Namely, that this micromotion heating, or the degree of heating by this micromotion, also depends on the mass ratio of the buffer gas to the ion. Yeah, and that has first been discussed in this seminal paper by Hans Dehmelt already in the 1960s. That where it was explained that the buffer gas should not be too heavy. Yeah. So meaning the ideal situation is if you have a light buffer gas and a heavy ion, then this problem of micromotion heating of the ions through the collisions is not a problem actually, or a lesser problem, and you can still get efficient buffer gas cooling. But if under conditions where the buffer gas is heavier than the ions, then you essentially don't get cooling, but in many cases you can get heating. And that is also shown here in this plot here, where we have performed the simulation of a cold ion in a radio frequency trap. And just looking at 25 ion neutral collisions with a buffer gas, which was assumed to be in the simulations at 0 Kelvin for different mass ratios. And we were looking at the distribution of ion energies after 25 such collisions. And that one can see that as a function of the neutral to ion mass ratio, right? So for the distribution gets ever broader after these 25 collisions. So the heavier the neutral compared to the ion, right? So the broader the energy distribution of the ion gets after these collisions, even if we start with very cold ions and very cold atoms. And the reason is just this coupling of micromotion energy into the secular motion of the ion. So all of this needs to be qualified a bit, right? Because it also turned out that the degree of heating and cooling is also sensitively dependent on the shape of the ultracold atom cloud. And the first one to point this out was actually also again our chairman Sadik in this paper from a few years ago. Where it was essentially shown that if you have a localized atom cloud, right, say in a MOT, right, and if you have an ion whose initial trajectory is much larger than the extent of this atom cloud, then you can still get buffer gas cooling, even though the buffer gas is much heavier than your ion. Yeah, so these are localization effects that also play an important role here. Okay, so that has become a big topic in recent years in the field. And one experiment to first explore these kind of phenomena really in the ultracold regime is this seminal work from Roy Ozeri's group, which was the first hybrid trap experiment where they really managed to combine ground state cooled ions, so ions which have been cooled down to the motional ground state of the ion trap with ultracold atoms. And in this experiment, they had strontium ions paired with ultracold rubidium atoms, and they were cooling down the strontium ions to the ground state of the trap, and then looked at collisions of these ground state cooled ions with the rubidium atoms in the trap. And we're then exploring the energetics of these collisions and the ion energy distributions. So what it turns out is that that the energy distribution that the ion assumes because of this micromotion heating during the collisions, these are not thermal distributions, right? Because it's not a system in thermal equilibrium, right? The system is always driven by the RF fields. So it's non-equilibrium thermodynamics that we are talking about here. And it turns out that the ion energy distributions that one gets here, that they can be understood in terms of a so-called Zallis distribution. Yeah, Zallis distribution, this is a generalized distribution which can be written down in different ways. One is given here from this paper. And so these are energy distributions that one gets from non-equilibrium systems, which under certain conditions can then assume the form of Boltzmann distributions again. But whenever one has such Zallis distributions, it's an indication that one is not really in thermal equilibrium. And a few years ago, we also showed that one can, starting from some very fundamental considerations, can prove that for the case of an ion atom hybrid system in an RF trap, we really have to arrive at something like a Zallis distribution. Okay, so what they then did is in this experiment, they had this strontium ion in the trap, in the ground state, and then interacted with the ultracold rubidium atoms. And after a few collisions of an ion with atoms from the ultracold rubidium cloud, they would then determine temperature is a bad word here to use, but they would essentially map out the energy distribution, the kinetic energy distribution of the ion in the trap. And they were doing this by Rabi thermometry on a quadrupole transition in the strontium ion. So essentially the same type of thermometry technique that I was also already explaining in my first lecture, which, for instance, we used in our own group for measuring coherent motion excitation of calcium nitrogen ion strings, right? So these were spectroscopic experiments done in the resolved sideband regime, and were looking at sideband transitions of this ion on these narrow transitions, and they were driving Rabi oscillations, and from the amplitude and the frequency of these Rabi oscillations, they could then essentially work out the ion energy distributions in the trap after collisions with the ultracold rubidium atoms. And these were typical results that they got. You see, this was a typical Rabi oscillation for an ultracold ion before the collisions, and this is what they got after the collisions in the different sorts of experiments. And then they were modeling these Rabi oscillations, first assuming just a thermal distribution of the ion energies in the trap, and then a Thales distribution. And one can see that the Thales distribution fits the data much better than the thermal distribution. So this already suggests that these ions that are after the collision is not thermally distributed, right? But it's a non-thermal distribution which can be well modeled with the Thales distribution. And they were then determining ion temperature as a function of the number of collisions that they had between the ions and the atoms in the trap. And what they found out through all these experiments is that even if they start with the perfectly ground state cooled ions and with ultra cold atoms in the trap, in the end, what they arrived at is that the steady state temperature of the ion in the trap after all these collisions was not what corresponds to the ground state of the ion in the trap, but to about 7 millikelvin. Yeah, so it's quite high. And the reason was this effect. This was this micromotion heating of the coupling of micromotion energy into the secular motion because of collisions between the two species during the micromotion cycle, when the ions were pulled away from the RF null line through the interactions with the ultracold atoms. Okay, just to briefly wrap this up, let me mention a very recent experiment where they tried to circumvent this problem by choosing a very light buffer gas and a very heavy ion, lithium and terbium. And this is an experiment from René Herritsma's group in Amsterdam. And the objective here was really, okay, we really want to study ultra-cold collisions now. Yeah, so collisions where we only have a few partial waves left, yeah, where we are not in the classical regime anymore, but where we really want to see quantum signatures in the collision. And one big obstacle for reaching this regime was exactly this micromotion. So they implemented an experiment with a very light buffer gas and a very heavy ion, right, where these problems are minimized. And by doing so, they achieved exactly that. And this was really, to the best of my knowledge, the first experiment where they could see an ion-atom collision process close to the single partial wave regime, where in their case they looked at the spin flip process in the terbium ion, where they could really see a non-constant spin flip probability, which is attributed or was attributed to quantum features in the collision, right? In this case, so-called resonances, right, which modulate the spin flip cross section at certain collision energies, right? So this is a very nice experiment, a heroic feat, if one can say, where they really managed to drive ion-atom collisions to very low energies and start seeing quantum features in ion-atom collisions. Okay, so I think my time is already up. I will therefore skip the very last part of my lecture. Shall we do that?
Yes, yes.
Yeah, okay, very good. So just very quickly and very briefly, all of the experiments that I have been talking about so far were dealing with atomic ions and ultra-cold atoms. And a couple of years ago, we and also other groups, we started to introduce sympathetically cooled molecular ions. into this hybrid trap experiments. And so let me just show you a few results and phenomena that one can observe here. So specifically what we had been looking at is charge transfer dynamics, now including molecular ions like N2 plus and O2 plus with the ultracold rubidium atoms. And again, what is important here is the N2 plus and the O2 plus molecular ions, they were sympathetically cooled in our experiments. And they were all always in the ground state, in the electronic ground state, but the rubidium atoms, they were in a mod in our experiment. So we again had collisions in the ground state and in the excited state. Okay, so we now also did a slight upgrade to our experiment in order to be able to be more precisely tune collision energies, right? Because we've already seen the collision energy dependence of these processes is a very important is of large interest in this whole discussion. And what it is, we came up with what we call a dynamic ion atom hybrid trap, where we did not overlap the mod with the ions in the center directly, but we produced the mod off-site the ions, and then we used a laser beam to exert radiation pressure on the ultracold atom cloud to push them through the ions and recapture the atoms on the other side. And then we were pushing them back and forth, right, at well-defined velocities. And in this way, and by changing the intensity of this push laser beam, we could accelerate the atoms to different extent and therefore precisely tune the collision energies in these experiments. And this is a much more precise way than tuning collision energy by just imparting micromotion on the ions. Okay, so this is a movie which shows this atom cloud flying back and forth between the two extreme positions in the trap. So let me just quickly tell you a few of the phenomena that we see here. Let's focus on the case of N2 plus rubidium. So the process that we are looking at is N2 plus colliding with rubidium, either in its ground state or in the excited doublet P3 half state. And the product of this collision is then a rubidium plus ion, so it's a charge transfer, right? Plus nitrogen in some excited electronic state. And it's important to realize that nitrogen and rubidium have vastly different ionization energies. So the energy liberated by this charge transfer is quite high, right? You can see it's on the order of 100,000 centimeters to the -1 or 13 eV, whatever you prefer. And so we produce nitrogen in highly excited electronic states in that way. What we are now measuring was charge transfer rate constants for this process, both with rubidium in the ground state and with rubidium in the excited state. And what we saw here also was that there's a massive difference, right, in the rate constants between collisions with rubidium in the ground state and with rubidium in the excited state as a function of the collision energy, and also the energy difference seems to be quite different. Now, what is the reason for that? Let's have a look at the process in the excited state first. So here the rubidium is in a doublet P3 half state, right? So this means this can't be viewed as a structureless particle anymore, but it is because we have one electron in the p orbital. So the valence electron is in the p orbital. So this is not spherically symmetric anymore. So this means that we do have a permanent quadrupole moment in this state. And that means we have a C3 coefficient, right, in the interaction potential. And this manifests itself in the rate constant. The rate constant that we measure is on the order of 2 × 10⁻⁸ cubic centimeters per second. And the Langevin rate constant is a factor of 4 lower, right? So we have a process that is considerably faster than Langevin. So we have to take into account this C3 coefficient now. And one can then predict the classical capture rate constant as a function of the collision energy, right? Taking into account the C3 term. And one can see that in the Langevin case, only the C4 term, we have a rate constant that is constant with the collision energy, but including the C3 term, we now have a rate constant that strongly depends on the collision energy. And at room temperature, right, say, or collision energies that correspond to room temperature, there is little difference between them, but at 20 millikelvin or so, where we were in this experiment, right, there is really this factor of 4 difference. And this is a comparison with the experiment, and you can see that it agrees very well. So at these low collision energies, these 3 coefficient really becomes important. So in the ground state, with rubidium in the ground state, we have a rate constant that is slower than longitudinal, right? Lower than longitudinal by a factor of 3, right? So this means that it can't really be understood in terms of capture dynamics anymore, but we have to also look at the short range part of the collision, right? What happens at short range in order to understand what's going on. And so we did this through some rather extensive theoretical modeling together with colleagues from theory. And at this case, one really has to start looking at the potential energy curves again and how the states interact with one another. And it turns out that with N2++ rubidium in the ground state, we have the case where we come in on this red potential curve, right? And then it turns out that this curve intersects with a charge transfer state. And around these intersection points, again, we can have non-adiabatic charge transfer. However, what becomes important here compared to the atomic collision system is now that we also have an orientation dependence, right? Namely, how the rubidium atom is oriented with respect to the nitrogen molecule when they two approach one another. And one can see that the couplings between these curves is strongly dependent on the orientation angle between those two, between the two collision partners. So to cut this long story short, what one gets out of this is that the collision dynamics is in fact rather complex. And what goes on here is that if the two collide with one another, they enter on the red curve, right? And then they can be trapped in this potential well for some time. And during the time they are trapped here, they can undergo multiple collisions or multiple crossings between the two curves. And only if they find themselves at the crossing on the black curve on an outgoing trajectory, then they can undergo a real charge transfer, right? And the probability for this is not 100%, and therefore we in the end observe a rate constant that is lower than longitudinal. Okay, so this means that in these molecular systems, short-range effects also become very important then. So I already see Sourav becoming restless because I'm taking up too much time. I think I'll stop here.
So, yeah, thank you very much, Stefan.
Thank you very much. So it was a great pleasure to be here.
Yes, Stefan.